Applications of X-ray crystallography. There are many different applications that use X-ray crystallography. Here we will explore a few of them, such as structure-based drug design, materials and earth science, outside-of-the-box techniques, as well as the future and beyond applications of X-ray crystallography. Structure-based drug design. Here, we briefly introduce how people utilize protein structure to design a new chemical molecule and use it for drug development. In most cases, people would try to find some potential binding sites on the structure and use computers to calculate the possibility of certain molecules binding on these sites. After that, we can get several possible molecules which combine and inhibit the activity of the protein. Next, people have different methods to modify the structure of the molecule they found. For example, they can try to link two or more closed small fragments, or they can extend the molecule so that it can bind on the site much tighter. After modifications, scientists can take these new synthesized molecules to do further experimental tests and complete preclinical trials. In the beginning, researchers successfully solved several crystal structures of kinase protein with different small chemical compounds. Among these co-crystal structures, they found that structure A is the most basic scaffold structure of the inhibitor candidate. In addition, they found a correlation between structure and binding affinity. Adding atoms in the ring may increase its binding affinity, so they synthesized a group of compounds with different modifications on the ring. PLX4720 is one of these modified compounds that was further modified to the final drug product. After sequential affinity, selectivity, anti-cancer activity test, they got into clinical trials in 2010 and received FDA approval in 2011 for treating the late-stage melanoma. Materials and earth science. Geologic thermometry. In some minerals that have become ordered after existing in a disordered state, a condition is found in which the basic structure is essentially a single crystal, while the superstructure is divided into small domains whose orientations, although bearing a rational relation to the more highly symmetric basic structure, are dissimilar. The presence of these domains can be detected by X-ray diffraction and can be used as an indication to the previous temperature history of the mineral. It has been shown that when certain minerals transform from a high-temperature form to a low-temperature form of lower symmetry, domains of related orientations are formed. The presence of these domains is easily recognized on the X-ray diffraction orders of specimens with a high-temperature history. Materials. Framework materials have been utilized as a scaffold for ordering molecules for analysis by diffraction methods in canvas areas for future exploration. Open framework materials, such as metal organic frameworks and coordination polymers, have been widely investigated for their gas absorption and separation properties. However, recent studies have demonstrated that their high crystalline structures can be used to periodically organize gas molecules and non-structural metal compounds either within their pore voids or by anchoring to the framework architecture. Accordingly, open framework can act as a matrix for isolating and elucidating the structures of these moieties by X-ray diffraction. This concept has broad scope for development as an analytical tool where obtaining single crystals of a target molecule presents a significant challenge and additionally offers potential for obtaining insights into chemically relative species that can be stabilized within the pore network. The real bottleneck effect of X-ray crystallography in structural biology is crystallization. If a small protein just does not cooperate, no matter how hard you have tried, you might want to check out the following mind-blowing study before surrendering to NMR. Here are some techniques that are outside of the box. No space groups with mirror planes? No problem. In this pioneering work, carried out by Dr. Kent and colleagues, published in 2008, the author chemically synthesized snowflake antifreeze protein and mixed it with naturally occurring L-snowflake antifreeze protein during crystallization. Protein crystals appeared rapidly only from a solution containing both enantiomers, but not for L-protein alone when screened under the standard set of crystallization conditions. Several other studies using the same methodology have been published since this one, suggesting that this unorthodox strategy is legitimate. If you are getting tired of routine protein purification and tedious screening for crystallization conditions, you might want to check whether these overexpressed proteins already formed crystals inside the cell. So far, people have shown that calcineurin, firefly luciferase, alcohol oxidase of a methytrophic yeast, among others, could successfully crystallize in vivo. It is still very rare for crystals to form in cellulo, but it might be a potential direction for the next methodology breakthrough, especially given the technique we now have to collect data from small protein crystals. Future and beyond. These are just a few of the pitfalls that exist with X-ray crystallography today. However, some new techniques have been created which eliminate these pitfalls. These techniques will be shown in the next slides. Free-electron lasers. In order to combat the negative effects of X-rays, better X-ray sources have been developed, including free-electron lasers. Free-electron lasers have very high-speed electrons moving freely through a magnetic structure, which allows it to be tunable and have frequencies ranging from microwaves to UV rays and X-rays. The laser uses pulses which prevent destroying the crystals that are being imaged. The direction of the beam is in the longitudinal directions, and the way in which the magnets are arranged is called an undulator, as it forces the electron beam to move transversely along a sinusoidal path about the axis of the undulator. With the development of free energy lasers, femtosecond crystallography began to develop. Femtosecond crystallography focuses on microfocus X-ray pulses that are femtoseconds long, which can probe nano or micrometer-sized crystals each individually. Overall, we can get a clear molecular structure without the radiation damage associated with other crystallography techniques. To use femtosecond crystallography, we can use crystals that are much smaller in size, so microcrystalline FID method was designed. In this method, a denser precipitant is dropped through a protein solution. At the interface of these two solutions, a microcrystal pellet forms. This solution is then used to perform femtosecond crystallography. Here's a schematic representation of an experiment using femtosecond crystallography. The nanocrystals are contained within the mother liquid, which is delivered into the X-ray beam by a gas-focused liquid injector. The X-ray beam, which is transverse to the jet, hits the crystals in the interaction region. Diffraction snapshots of single crystals are recorded using the pixel array detector located in the forward scattering region. This method differs by the use of multiple crystals to obtain the final structure. Here's a case in which femtosecond X-ray free electron laser pulses were used to obtain structural measurements of crystals in which they could time when the binding of the ligand would occur through diffusion due to the size of the crystals being used. 4 different structures were discovered which varied from the apo state to ligand-bound intermediate and then the final ligand-bound state. This study showcased the ability of using micro/nanocrystals as well as using mix and inject time-resolved crystallography with FEL lasers. Here are the different crystal structures of the different states of the protein, such as the apo, the intermediate, as well as the ligand-bound state, which go in obvious conformation change. Automated protein nanocrystallization. Equipment like the Phoenix have been designed to set up crystal trays very quickly and efficiently. The use of these robots allow for crystal plates to be made on a much larger scale if need be, or on a small scale in which small amounts of protein are needed. SONICC technology relies on UV light and two-photon excited fluorescence to detect crystals. Crystals appear white against a stark black background, helping users identify crystals even in cloudy conditions. This technology can distinguish between salt and protein crystals, as well as detect submicron crystals and facilitate the detection of crystals in lipid cubic phase. The SONICC will allow detection of virtually any crystal form, such as microcrystals, that are hiding behind precipitate, or even crystals placed on the edge of the protein drop. The use of the SONICC in the sonic imaging that occurs is pictured in the picture on the right.